My name is Julia Dennis, and I'm an early college student majoring in general engineering.
Hi everyone, my name is Nikitta Joan, and I double major in aerospace engineering and computer science. Today we're going to be talking about Hermit Box game analysis. Our project mentor was Dr. Dong, and this is our summer project. So, today's outline. Combinational games. We're going to be talking about what they are and how they're formed. Then we will move into partisan versus impartial games. Then we will be looking into outcome classes. Then, moving on, Hermit Box game rules and characterization. Then we will show you game tree charts of 2x2 and 3x3. Then we will be talking about dominated positions and reversible positions. And lastly, I will be talking about the conclusion and the future work of this project. So, Julia, what makes a game combinatorial?
Well, combinatorial games are a specific type of game that we are able to analyze and decide whether they are first-person wins or second-person wins, or if there's a specific strategy. So, like she said, what makes a game combinatorial? First of all, the game has to be a two-player game. The game also has to be deterministic, which means there's no type of randomization, including rolling dice or picking a card from a deck. The game also has to have perfect information, so both players has to know everything about the game, including what moves are available to the other player. They also have to know everything about the game state. And at the end of the game, there has to be a clear winner and a clear loser with no chance of either players ending up in a tie. So there are two types of combinatorial games, partisan and impartial games. In partisan games, some moves are available to one player, but not the other player. It's super common for games to have one player be able to move a specific color piece while the other player moves a different color piece. For example, in chess, one player moves the white pieces while the other player moves the black pieces. In impartial games, all moves are available to both players. For example, in dots and boxes, both players are able to make the same moves, so any restrictions that apply to one player also apply to the other player. So games end up in certain outcome classes, which Nikitta will now explain.
So now, there are 4 types of outcome classes: the endgame, the P-game, the L-game, and the R-game. The endgame, a game state in which the next player can force a win. So only the next player here can win the game. The P-game, a game state in which the previous player can force a win. The L-game, the left player can force a win regardless of who moves first. The R-game, the right player can force a win regardless of who moves first. So here we can see the happy faces and the sad faces. So what are they? In the end game, both players are happy. In the P game, also known as a zero game, both players are sad. In the L game, which is also the positive game, only the left player is happy. In the negative game, the R game, only the right player is happy. Moving on. We're going to be talking about Hermit Box game rules. Here, only 2 players can move on the board with 3 colors. Boxes of the same colors cannot be kept together. So on the crosses that you can see on the screen, on the figure 1, blue box cannot be kept around these boxes. The first player unable to make a move loses the game. So, what are the game characterizations in Hermit Boxes? It is, like Julia said, it is an impartial game. Both players have the same kind of moves. If the left player has a winning strategy going first, then the right player also has a winning strategy going first. Similarly, if the right player has a winning strategy going first, then the left player can use the same strategy and win. The outcome classes for this game is only the first player win and a second player win. So now I'm going to be talking about the 2x2 with the 2 colors. So here we have the first player moving vertically on the right corner, as you can see on the right, and the first player makes a red block move. I'm sorry. I'm just going to be reading this out. So here we have the first player moving vertically on the top right corner, and towards my right, you can see the first player is moving horizontally from the top left corner. Notice how we don't use this same move towards the next move. And then we can see that the second player uses the yellow block and moves down. Similarly, for the 2x2 with the 3 colors, it's the similar type of game chart. However, on the third level of the game, you can see that the first player wins the game. Now Julia will be explaining dominated positions.
So our game trees can get very large very fast, so we need specific ways in order to cut them down. So dominated positions in Hermit Boxes are a specific way we can cut down our game tree. So here in the top left, you can see a game state where in the middle there's a vertically placed yellow block, and in the top left and top right there's a vertically placed red block. You can see that our player can make 2 moves. One move is horizontally placing a red block at the bottom, and move 2, vertically placing a red block in the bottom left. We can see that in move 2, there is still one more available move by placing a vertically placed red block in the bottom right corner. But in move 1, there's no more available moves that the next player can take. So if we look at move 2, we can see that our player, the first player, leaves one more move available. So the second player is able to take that move, and then the first player has no more moves available. But in move 1, since there's no moves left, the second player automatically loses. So when looking at these 2 moves, we can see that move 1 is a far better move than move 2 because it automatically lets our player win, while move 2 automatically has our player lose. So when making our game trees, we cut out all games where our player does not act in their best interest. So we would cut out move 2 and all moves like it because that would be not beneficial to our player. So here we're going to move on to a game tree. As you can see, it's very large. It's a 3x3 game tree using only 2 colors. You can see that the first 2 moves that we have our player making, there's only 2 of them, although you can probably think of a lot more moves that our player can make. But those moves are the best moves for our player to make, so we only include them. Below that, we can see all possible moves that the second player can make, and below that, how our first player can win from those moves. So moving on, there's one more method that we can use in order to cut down our game trees called reversible positions. This one is a bit more complicated than our dominated positions, but we'll start slow. We can see on the left that there is a game that is being played out. First, no moves taken, then the first player moves in the center, the second player moves in the top right, the first player moves in the top left, then the second player moves in the bottom left, and then the first player moves in the bottom right, and then from then on, there's no more moves available, so the game is over. So if we look at these, we can see that I've labeled 3 of the moves as state G, state G1, and state G2. If you look below state G, we can see that I've labeled it P. If you remember from Nikitta's talk, that is outcome class second player win. If you also remember, we consider P to be equal to 0. If you look at state G2, we can also see that it is also worth a value P, meaning that it is also worth a value 0. So state G and state G2 are pretty much the same equivalency for how much they're worth. So using reversible positions, we can cut off the game tree right above state G and replace it with the game tree below state G2. But since the game is over after state G2, we can essentially cut off the game tree right before state G, meaning we can shorten the game tree by a lot. Over here, we can see that it's down to 3 moves. That way we can cut down our game trees by a lot, which would be very useful in much larger games. So here we can see the previous game tree, but it's cut down a lot using reversible positions. And now Nikitta will talk about our conclusion.
Coming into the conclusion, we have 2x2 and a 3x3 chart with 2 colors and 3 colors. In a 2x2 chart, the second player wins, so it's a P game state. In the 3x3, in a 3 colors in a 2x2 chart, the first player wins. And in the 3x3, in 2 colors, the first player wins. However, for 3 colors in a 3x3 chart, we were not able to compute as it was getting larger and larger. However, with Professor Dong's help, we are going to assume that it's a second player win. Our future work for this project is analyzing the 3x3 chart and then going into the 4x4 game board with 2 colors and 3 colors. Then we cut down the game tree size by symmetry, dominated positions, and reversible positions. Then we can further analyze this by using a software called Combinational Game Suite, CG Suite in short, for Hermit Boxes. These are the references we used, and we'll be taking questions.